Okay, you might have noticed the homework number 2 is out since yesterday, so and you have as usual 1 week for it. So due Tuesday. It's more homeworky this time in the sense that it's like midterm type of thing, like just examples you can work out on the paper, or ideally work out on the paper and then I'll techify it. Doran posted this nice beginner tutorial on LaTeX. Sort of cool thing. If you haven't done it before, you might as well try. Because that's way to typeset math really nicely, and it's almost guaranteed to be useful to you later on, especially if you'll be doing like theses or some write-ups involving some mathematics. Okay, that's that. So where we were discussing about eigenvalues and eigenvectors, and the last time I finished by giving you this example where eigenvalues and eigenvectors are useful. It's an example from stochastic processes, which is sort of cool. It's interesting in its own right? So as we are supposed to do lots of applications here, we can as well spend some time talking about it. So I guess let me go quickly again through the setup in case you don't remember it from the previous time. So we are looking at this model of a distribution of rental cars in the country. Okay, so or it could be really anything, just to give it some more concrete idea, right? So we are looking, for some reason we're interested, what is the percentage of cars in Denver as opposed to outside, okay? So this was the starting state, like at the time we started caring about the situation. 2% of all cars in the country were in Denver, and 19% were somewhere else, okay? And then I said that, like, you can imagine some statisticians came up with the following model, that every month 80% cars which are in Denver stay in Denver, and 20% of them leave, meaning from Denver go outside. And 5% come in, so from outside Denver come in Denver, and 95% stay outside. Sort of makes sense, right? Most of them stays outside. And the way we formalized it was, you can describe it using a Markov chain. Markov chain is essentially a graph where the nodes represent some states. In this case, the states are being inside Denver and being outside Denver. And the edges are oriented edges weighted with the transition probability, essentially. So what does it mean for our example? So it means if we are inside Denver, we have 0.8 probability of staying there. That's this 80%, okay? And we have 0.2 probability of going outside. And similarly, if we are outside, we have 0.95 probability of staying outside and 0.05 coming inside Denver, okay? So this is a very simple example of a Markov chain. And we can encode these transition probabilities in a matrix. I guess you can also look at it as like some little entities that are living in these states, like lots of ants or something like this. And every time, in this case it's every month, but it could be arbitrary unit of time, right? Every entity sort of rolls a dice, and depending on what number it gets, it takes the transition. So I guess the good term there would be a random walk, right, in the graph. So like you can imagine you have like million ants or something like this. Oops, it's playing with the focus. A little bit more focus. I don't think it's good. What was I saying? Oh, right. So if you start with some initial distribution there, and every time, here in every month, doesn't matter, rolls a dice, and they makes the transition based on what number it got on the dice, right? So that's basically exactly the same idea, okay? Okay, so the key to applying linear algebra is to formalize it using a matrix. So this is an example of a Markov matrix. I think the Markov matrix has the property that all the elements of the matrix are non-negative, and all the elements in every column sum to 1. So these two guys sum to 1, and these two guys sum to 1 too. And that's because we are accounting for all cars. Like no car like disappears, no car gets destroyed in this model anyway. Okay, this is formalized using this formula that like this one vector is just a vector of all ones, right? So if I transpose the vector of all ones and multiply from the left with A, that exactly means summing the individual rows, right? And this partition of unity property of A means that if I do 1t A, then I get again 1t, right? That both of these rows, if I sum them as vectors, I get this once, okay? And now what does the matrix do? It basically performs the one step of the simulation, if you want to look at it this way. So if U0 was our initial distribution, okay, after applying the matrix once, what's going to happen? I'm going to compute what is the percentage of cars in Denver after one step, okay? Because again, look at it. What the matrix multiplication does is this, right? So 0.12 were the number of cars that were in Denver, and out of them 0.8 stayed, right? And we need to account for the ones that came from the outside. So it was 0.98 outside with 0.05 probability of coming in, okay? So this is the total number of cars in, okay? Similarly, this multiplication tells us the number of cars outside. And what I discussed the last time was that the U1 vector, the distribution after one step, after taking one iteration of the Markov chain, it will still be a partition of unity, meaning that if you sum the elements of U1, you get 1, okay? Or written in the language of linear algebra, 1 TU1 is 1. So this 1 is like a vector 1, and this 1 is a scalar 1, but I hope you got that. And that's true in general. That's true in general because of this calculation, right? So if I do 1 TU1, I can write the U1 as A U0. But then I can do first 1TA, but because A is a Markov matrix, then 1TA is just 1t, right? And 1tu0, I assume that u0 was a distribution in the beginning, so this is 1, okay? So that means that 1tu1 is also going to be 1. If I'm going to take a next step, I'm going to compute a squared u0. If I'm going to simulate another month, I will do a cube and so on, right? So after k steps or k months in this example, I will get a to the power of k times u0, okay? From this, you can see that's always going to be a distribution, because in our model, no cars are disappearing, so it's always summing to 1. It's just the proportion outside versus inside, okay? And what we are interested in, we want to figure out what is going to happen in the long run. What is this a to the power of k u0 going to converge, right? Or what is this is the uk, right? I can write it like this. This is the state in the step k. I'm interested in what's going to happen for large k's. And I think that's where I stopped the last time. And the way we are going to find the answer is by computing eigenvalues and eigenvectors of the matrix A. Okay, so let's do that maybe on another paper. Okay, so let's first compute the eigenvalues and eigenvectors of the matrix A. I'm actually not going to be computing them. That doesn't make sense. I will just show you what the answer is. So there's one eigenvalue which is 1. By the way, one of the examples in your homework is to compute eigenvalues and eigenvectors. So I hope you remember the drill, how it works. You form the characteristic polynomial, find the roots of the characteristic polynomial. That gives you the eigenvectors, right? And then you find the corresponding eigenvectors as the vectors in the null space of the matrix A minus lambda identity. So here I already found the eigenvalues and eigenvectors for you, so we can move a little bit faster. So that's for this matrix A here. So what this means is that A v1 gives me, well, lambda 1 v1, but lambda 1 is just 1, so in this case the v1 just stays put, okay? And A v2 gives me lambda 2 v2, where lambda 2 is 0.75, okay? So notice this is the good case where the eigenvalues are not only real, but they are also different, right? And from what we had the last time, you know that in this case, the eigenvalues are different. The eigenvectors are going to be linearly independent. That's sort of obvious, right? Just by looking at it, you can see that this matrix would be invertible. And that means that in this case, that's the good case where the eigenvectors form bases, okay? basis is cool because it means that any vector from R2 can be expressed as a linear combination of the basis vectors, okay, including U0. Okay, so let's take a look at it. So U0 must be some combination of the basis vectors. So alpha and beta are some scalars. And for this particular U0, the 0.02 and 0.98, it turns out the alpha and beta, it turns out that the alpha is actually 1 and the beta is 0.18. If you want to do the calculations, you can. Yeah, the numbers, not so easy to do it off the top of your head, but with a calculator it would be easy to verify, I think. And else you can trust me, this is the case. So I can also write it as V1 plus 0.18 V2. I guess that's the price we need to pay for like putting there like a realistic looking numbers. That's always the funny part of like the homework or something, to like design it so you can actually get some like reasonable numbers, right? As you're like computing, you can get like crazy numbers quite easily. Okay, so that's interesting. So we express the initial distribution as a linear combination of the eigenvectors. Okay. So what's gonna happen after I do my first step? So after I do A U0. Okay, so that's the distribution after first month in my example here. Well, I already know that V1 and V2 are eigenvectors, right? So this will give me, okay, let me write it slowly. So this will be AV1 plus 0.18 AV2. And because they are eigenvectors, this is going to be nothing but lambda 1 V1 plus 0.18 lambda 2 V2, right? Where lambda 1, we remember, is 1 and lambda 2 is 0.75, okay? Well, in step UK, I have here a to the power of k applied to U0, right? So it's basically the same story. I can just like sort of copy paste it. I just keep applying the matrices over and over again, and what I will get here are the eigenvalues to the power of k, okay? Everybody cool with that? Yep. Okay. Well, then what's going to happen? So lambda 1 was 1, right? So the lambda 1 to the power of k is still 1, right? I can raise it to whatever power I want. It's still going to stay 1, okay? And lambda 2, that was 0.75, right? So what's going to happen with 0.75 if k goes to infinity?
0.
It goes to 0 very quickly, right? It goes to 0. So the limit of lambda 2 to the power of k for k going to infinity is 0. And it's actually gonna get to 0 very quickly, right? Already like for k like 10 or 20 or 30, it's gonna be like almost nothing. So what does it mean for the limit of the entire thing? So what does it mean for the limit of the vector? Limit uk for k going to infinity. Well, what do you think? What the limit is going to be? V1, exactly. Right, because this stays 1 and this very quickly disappears, so end up with V1. And V1, that's what we have here, right? That's 0.2 and 0.8 vector. And that's the steady state. That's what I was looking for. That's the distribution. If we let this system evolve after long enough time, you actually wouldn't even have to wait so long, right? Maybe like 10, 20, 30. But the point is that eventually it will get to this state. And it sort of makes sense that this is the steady state, right? Because this is the eigenvector corresponding to eigenvalue 1. So it means that if I apply the transition matrix A to it, right, AV1 is V1, right? So it doesn't really change it. So that's what I mean by steady state. Okay? By the way, there's one interesting thing. How does the initial distribution matter? Question. Slightly tricky question. What difference the initial distribution? What if there was like more cars in Denver to begin with? Would it make any difference? It wouldn't. It would make absolutely no difference, right? So all that really matters for the steady state, that's the interesting thing about Markov chains in general. The initial distribution doesn't matter at all. All that matters is the transition probabilities there, right? I guess the only difference it would make, like how quickly we will approach to the steady state, right? Because maybe it would take like longer if we start from some different initial. I mean, if we start already here, then we are already there, right? So that's obvious. Okay. Yeah, later we will sort of revisit this idea of Markov chains. I think that's gonna be when we'll be talking about PageRank. I think that's gonna be probably the last project we'll be doing. So PageRank is the Google, or at least the original Google algorithm, and that's based on exactly the same model. So this is sort of like a preview on like a toy example, and the PageRank is essentially applying the same model of like these ants traveling through some states. In the PageRank, these ants are like sort of like people clicking on websites, and the steady state distribution is like the probability of visiting a website. We'll get there later when we have discussed SVD and some other tools which we'll need for that. Okay. But here, this was like an illustration for you that the eigenvectors actually mean something. If the matrix is a Markov matrix, then the eigenvector corresponding to eigenvalue 1 is the steady state distribution. So that's actually something tangible, something that's immediately useful. Let's try to convince you that this is something that has some nice practical applications. Okay. All right, so I started talking last time about a little bit that sometimes there were problems with eigenvalues and eigenvectors, that sometimes matrices can be diagonalized, right? Like last time I think we were assuming the optimistic case. So you know that if all eigenvalues are different, that's what we proved last time. If all eigenvalues are different, then the eigenvectors are linearly independent and the matrix is diagonalizable, okay? Either in the real or complex domain. If you're lucky and the eigenvalues are real, then the matrix is diagonalizable in the real domain. If you are less lucky, then the matrix requires complex eigenvalues and eigenvectors. But if they are different, you can still diagonalize it in the complex domain, right? It's trivial that the real numbers are a subset of complex numbers. So on every real matrix, you can look at it as a complex matrix, right? And if it's not real, if it's not diagonalizable in the real domain, you still have a chance of diagonalizing it by switching to complex numbers. So that's good. Now there is still another catch, unfortunately, and sometimes even the complex numbers don't save the day. Okay, some matrices just can't be diagonalized, period, and you won't save it even by going to quaternions or octonions or whatever. And that's because the problem is elsewhere. So these matrices are called defective matrices, and here are two very simple examples of 2x2 defective matrices. So I claim that these matrices are not diagonalizable. By the way, notice that this is also not related to the rank of the matrix, right? Somebody was asking me the last time, how do the rank of the matrix relates to the eigenvalues and eigenvectors? But here you can see what's the rank of this matrix? 2, yeah, and this one? 1, right? So they both have different rank, but they are both defective. Neither of them can be diagonalized. So it hasn't really anything to do with rank. By the way, as we are talking about this, how is rank related to eigenvalues? The invertibility of the matrix to eigenvalues and eigenvectors. There is one fairly obvious relationship. Can you spot it? Let me ask you this way: how from, if you know all the eigenvalues of a matrix, how can you tell if the matrix is singular or not, if it's invertible?
There's the same number of eigenvalues as the number of columns.
Eigenvalues or vectors?
Vectors.
That's an interesting proposition. No, that has more to do actually with the defective matrices, the thing you proposed. No, the point, okay, so you can tell if a matrix is singular from the eigenvalues, okay. Well, okay, let me ask a different question. What does it mean for a matrix to have eigenvalue 0? Well, eigenvalues are this, right? Eigenvalue lambda and eigenvector v means that this is true, okay? And v must be a non-zero vector. I discussed this at length, so I hope you remember this. So what does it mean if the lambda is 0? Well, that means that I'm gonna get 0 right here. So that means that the vector v must be a non-zero vector because it's an eigenvector. So it's a non-trivial vector which is in the null space of the matrix, right? Well, then the matrix A must be singular, right? I can also flip the argument. If the matrix is singular, then what does it mean? That means that I must have some non-trivial vector in the null space, right? Let's call it x, such that x is non-zero. You see that, right? And then, of course, then x, that means that x is eigenvector with eigenvalue 0. Okay, so you can, I guess you can combine this in a statement saying that A, it's sort of trivial, right? But it's good to realize this. So A is singular if and only if 0 is an eigenvalue of A. Okay. So that's in the case of so this is useful to remember, but it has nothing to do with the defective matrices as you might otherwise think. So how can you tell if a matrix is defective or not? It's actually a little more subtle. You need to look at things that are called algebraic and geometric multiplicity. So let me explain that. What does it mean? So the algebraic multiplicity means that you count. So algebraic multiplicity of an eigenvalue is the number of times it appears as a solution of the characteristic polynomial, right? I'm saying that if you have a characteristic polynomial like this, x minus 1 to 100, then 1 would be an eigenvalue which is repeated 100 times, okay? So the algebraic multiplicity of this eigenvalue 1, if this is a characteristic polynomial of some matrix, would be 100, okay? Now, on the other hand, geometric multiplicity for an eigenvalue means the dimension of the null space of A minus lambda I, okay? Think about it for a second. The null space is how we found the eigenvectors, right? When we are searching for eigenvectors, we first find the eigenvalues. Once we know the eigenvalues, we can be looking for vectors in the null space of this matrix, and they are eigenvectors, okay? And of course, the null space can have all sorts of dimensions, right? And the dimensions of the null space of A minus lambda I is called geometric multiplicity. Okay? And this is how you can tell if the matrix is or is not defective. Okay? So it's always true that if I call this geometric multiplicity, and this is algebraic multiplicity, it's always true that the geometric multiplicity is less than or equal than the algebraic one. By the way, this is going like a little bit deeper into linear algebra, so I'm not going to be proving these things. We'd probably need an entire lecture just to elaborate on these things. But I don't want to. That's not the point here. I just want to explain the defective matrices. So just trust me, the geometric multiplicity is at most algebraic one. But sometimes it can happen that the geometric multiplicity is strictly less than algebraic one. Okay. That means that the dimension of the null space is actually less than the algebraic multiplicity of the eigenvalue. And in that case, we are dealing with a defective matrix. That's how you could tell. Okay? Now, yeah, repeated eigenvalues like in this case, they don't always have to be a problem, right? As you can trivially see from the identity, because identity you can diagonalize in many ways you want. And yeah. So what can you do with matrices that are defective, that cannot be diagonalized? There is something you can do. That something is called Jordan normal form. What you can do is you cannot find an invertible. So if I get a defective matrix A, you cannot find an invertible matrix V such that V inverse would be diagonal. What you can do is you can find a matrix V such that this will be a collection of Jordan blocks, which basically means every Jordan block is a diagonal, lambda, 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 and there are off-diagonal ones. Okay, so that's one Jordan block, there is another one, and so on. So it's like almost diagonal, except for like a few off-diagonal terms. Okay, we are not gonna go to that because I yet have to find an application of the Jordan normal form. It's like sort of cool, like linear algebra result. But ultimately, these problems will essentially go away when we switch to singular value decomposition, okay? Because all these problems of eigenvalues and eigenvectors, they will essentially go away with singular value decomposition. So that will be our way to deal with that. But just remember that not all matrices can be diagonalized, okay? That was my point. So we are discussing eigenvalues. It's good to realize the relationship between eigenvalues and the determinant. So let's assume we do have a diagonalizable matrix. So the lambda would be a diagonal matrix here. And then we can find a nice relationship between the determinant and the eigenvalues of the matrix. Okay. So now we have to remember what we discussed about determinant. This is the one rule I definitely want you to remember. That's the product rule. That doesn't matter if we first do the product of A and B and then take the determinant, or if we first do determinants and then multiply them as scalars. Okay. So if we apply to the eigenvalue decomposition of a matrix, the V lambda V inverse, we get this. Okay. Here we use the other rule which I discussed when we are talking about determinants, that the determinant of an inverse matrix is the inverse of the determinant. Remember that? You look like you don't. I mean, that's okay. I'll show that again. That's really simple, right? Because if you take determinant A inverse, which is identity, right? Again, applying the product rule, is determinant A and determinant A inverse, which gives you the determinant A inverse with 1 over determinant A. We had this when we discussed determinants, okay? So that's what we apply here. Note that V is invertible, so this is cool because the determinant was not 0, so I can actually do that. But then what I can do with this, because these are just scalars, determinants are just scalars, okay? So they commute, right? So what I can do here is I can just write determinant V. Let me write it here. So this is equal determinant V inverse, and determinant lambda. Actually capital lambda, right? Because it's a matrix. So I can commute because these are just real numbers. Okay. If they were complex numbers, I could still do that. So this is again determinant V inverse, determinant lambda, right? But this is identity, so the determinant of that is 1. So that goes away. So this is just the determinant of lambda, okay? So what did we get here? We got that the determinant of A is equal to the determinant of lambda. But what was lambda? Lambda was just a diagonal matrix of eigenvalues, right? So lambda was this, to lambda n, okay? The V and lambda, that they could also be complex. If you cannot diagonalize it in the real domain, maybe you need to go to complex domain, but everything is cool, okay? Everything still works. So what is the determinant of this matrix? That's something very simple, right? Do you remember that? I hope you do. Determinant for diagonal matrix, yep. Exactly, it's just the product of the diagonal terms, right? So if I should write it here, the determinant of the matrix lambda is just lambda 1 times lambda 2 up to lambda n, okay? So that's actually something interesting, right? Because it tells us that the determinant of the matrix is actually equal to the determinant, to the product of the eigenvalues, right? The determinant, the matrix of the eigenvalues, product of the eigenvalues, okay? Which is quite interesting because computing the eigenvalues is sort of difficult, right? You have to find a characteristic polynomial and solve it. Well, that's not how you would be doing it, by the way, for large matrices. You would be doing some, you'd be using some different algorithms like power iteration and so on. But it's still complicated. Now, if you can instead compute the determinant, or you know the determinant already, then you immediately know at least the product of all the eigenvalues. Okay? There is another important concept, which is trace of a matrix. It's useful not just in relation to determinants and eigenvalues, even that's what I want to talk about now. It's a nice little tool in linear algebra. So let's take a look at it. So if you have it assumes a square matrix. It could also be complex, doesn't matter if this is real or complex, by the way, but let's just put here real. And what the trace is nothing special really. Trace, it is very dumb, right? It's just the sum of diagonal elements. Okay, so it ignores all the other elements of A and just sums all the diagonal elements. So in terms of like function notation, trace is a function of the same signature as determinant, right? So it takes a square matrix and produces just a single scalar. Okay. Do you see like the similar, like, okay, let me put it here to make it really obvious. That's the similar idea as determinant, right? Because determinant also was a function from a square matrix. So it was producing a number. Okay. There's a stark difference because the determinant was really a pain to compute and the trace is like a joke to compute, right? Nevertheless, the trace also gives me some information about the matrix and it's actually sort of cool. In terms of eigenvalues, it gives me some very interesting complementary information. I will let you guess what that could be. I will get to it later, but I will first discuss some properties of the trace, which are quite useful when we are doing like physics-based simulations. Some of the like physics-based models are elegantly expressed using traces of a matrix. So this is something that actually does come up. Even though it seems like so simple that doesn't really matter even to you. But the reason why trace is interesting is that it has lots of interesting algebraic properties. Okay, so let me go over a few of them. So the first is sort of obvious. If I transpose the matrix, I don't change the trace, right? Everybody believes me? Yeah, it's nothing really, because the diagonal doesn't change, right? And so only the numbers that actually don't matter in the trace do change, okay? Now, what is cool is the trace of a matrix product, ATB. Okay, so if I have two matrices, and the matrices, they don't even have to be square in this case. They can be m by n. But what I need is that they have both the same dimension, right? So both A and B, they are both m by n matrices, okay? Well, let's take a look. Okay, this is the final formula, but let's take a look at it, how we can derive it nicely. So let's say that A is matrix that looks like this. So the columns will be A1 to AN. Okay, so m by n matrix. And B would be another matrix of exactly the same size, but now with columns B1 up to Bn. Okay. So what's going to happen if I take the trace? Let me just write it as dr, so I don't have to be writing trace all the time. So if I have a trace of A transpose, if I transpose A, I will get A1t up to ANT, right? I just flip the role of rows and columns. And here is just B, okay? So my B columns. So do you see what the trace is of this product? That's where the usefulness, that's where the utility of traces really comes up when you are looking at traces of matrix products. So do you see what is the trace here? So sort of neat. So the trace is the sum of diagonal elements, right? And we are looking at the diagonal elements of a product of two matrices. And I sort of chose this layout to make this, to give this product a very elegant form. Sorry. So the result is that this is just a sum of all the dot products, right? So sum over I, AI transpose BI. Yeah, you see that? Because the number one element on the diagonal would be A1T B1, right? The second one would be A2T B2, and so on, right? So this is just a sum of the dot products, okay? So do you see what it means in terms of the original matrices, the trace ATB? Could you give it some, like, could you relate it to something else, you know? So this is the sum of dot products of all the columns, right? One at a time, right? So this is actually something very basic. This is basically a dot product on matrices, if you think about it that way. So let me put it a different way. If I unroll the matrix, did I talk about the vectorization operation? The vec operation? Yeah, I did. So if I unroll the matrix A like this, so I take the columns and I stack them like this into like one gigantic column vector, right? If I did the same for matrix B, well, I guess this is the same, B1, Bn, right? Then the trace of ATB is nothing but the dot product of the vectorized versions of them. Okay? So it's basically like a dot product on matrices. That's what we were dealing with when we were doing the DCT, right? When we had to convert a matrix to a vector form. But you can take a dot product directly on matrices. That's what a trace ATB does. By the way, in tensor notation, this is sometimes called double contraction and denoted like this. Is it called double column, or how is this symbol called? Double column. Column. Okay, yeah. So these two dots. Sometimes this is the same thing. This is just trace ATB, but like in some papers, in particular from Caltech, you can find this. It's because this goes to more general tensor notation. So I guess they like prefer to talk in general about tensors. It's the same thing. Okay, trace ATB. It's a useful thing. So that's what I have here. So yeah, if you want to write it out per components, you just do this. Okay. So you just take every element from A, multiply it with the corresponding element from B, and then sum it all together. And effectively, it's the inner product of the two matrices, okay? And again, interesting special case is if you take B to be just A, okay? If you just do ATA, trace of it. That's a very useful concept. In particular, if you take the square root of it, right, which you can because this is obviously going to be non-negative, this is called the Frobenius norm of a matrix, okay? So this is the analog of a norm. We always had the Euclidean norm of a vector, right, this thing here. And the Frobenius norm is essentially the direct extension of the Euclidean norm of a vector to a matrix, okay? So Frobenius norm of a matrix. Again, the Frobenius norm, if I write it like this, it's again type-wise the same idea. It's a function that maps from, I guess it doesn't even have to be square, right? I can just put m here to a number. So it's essentially like the length of a matrix or something. For example, if you are in MATLAB and you want to check that you got a zero matrix back, right? You have some calculations and you want to check if you got like a zero matrix. You cannot really directly test if you got all zeros because maybe you have some 10 to minus 15, right? Because there are rounding errors. But what you can do is you compute the Frobenius norm of a matrix, and if that's close to zero, then you are pretty much guaranteed that the entire matrix is close to zero. Yep.
Well, how can you get a trace of rectangular matrix?
You can. That's not defined. The point is that ATB is a square matrix, right? Because AT is n by m and B is m by n, so this is an n by n matrix. I guess you could define a trace of rectangle, but then it wouldn't have the nice properties. It would be sort of useless, I think. Wait, I don't think I've ever seen that. Okay, so what's next? Aha, there is more cool properties of the trace, actually. The trace is very useful. So if I have two square matrices, this is a very interesting thing, that I can actually swap the order of multiplication if I'm inside a trace. Yeah, I think I can just explain it this. So if I have two square matrices, C and D, if I take the trace of the product of C and D, it turns out that I can actually swap the order. Let's see why. It's pretty cool, right? Because in general you could not possibly do that. But well, let's look at, so what is the element? So again, we are looking at a matrix product, right? And trace looks at the diagonal, right? So if I have an element at row I and column I of the matrix product CD, if you remember how matrix product was defined, well, then you remember that was defined like this. That was Cij and Dji. Okay, so that's exactly what is this sum. And this sum is due to the trace saying that you are summing over all diagonal elements. Okay, so that's where this formula came from. Now what I can do, these are of course real or complex numbers, so they are commutative, right? So I can flip them, and I can also flip the order of the sums. And here I got nothing but a trace of DC, which is cool. So even though CD, of course, is in general not equal to DC, by the way, under what circumstances would DC and CD, under what circumstances matrix multiplications commutes?
Inverses of each other?
Yes, that's true. That's one case. Huh. So maybe I don't know the full answer to it, right? The answer, huh? So let's think about it. So of course, in general, CD will not be equal to DC, right? Under some special circumstances, it could be, right? You pointed out that if D would be the inverse of C, then yes, then they do commute, right?
If each of them are symmetrical?
If both of them are symmetric?
Yes.
I don't think that would cut it. What you would probably get the
Yeah, because
no. No. Here is a counterexample to that. If you have like 1, 1, 1, 1, and then you have another symmetric, which is like this, but if I multiply it, I get this, right? And if I multiply the other way, I would get 2's here and one's over there. Anyway, sorry, I don't want to digress too much. I guess. Okay. Anyway, so. Okay, no, we should not be discussing this case now. We can return to that later. So my point was that in general, it is not commutative, certainly, right? But after you take the trace of it, it is absolutely always commutative in the sense that the trace of CD and trace of DC is the same. Now you need to be a little bit careful, because then you get a little bit too excited, and then you could say that the trace of A, B, C, if I'm taking a product of 3 matrices and they are all square, but you need to be careful, because this would not be true. Trace A, C, B. Okay, if I have 3 of them, you cannot flip the order arbitrarily. What you can do is exactly what's written here, and that's all you can do, right? So you can either look at it as A, B, C, and in that case you can flip the order as B, C, A, okay? Or you can look at it as A, B, and then C, right? In which case you can flip the order like this, C, A, B. But this one is not there. You cannot flip it arbitrarily. It just follows from this rule. Just wanted to warn you that you can't get too happy about this rule. But nevertheless, this is very cool. Like I've seen lots of derivations in like, I guess, elastic energies in continuum mechanics where this is very useful. Okay, and my final point about traces is how does it relate to eigenvalues, because we are now talking about eigenvalues. And there's a very cool relationship between the trace and eigenvalues if we have a diagonalizable matrix. Okay, so similar to the case I discussed before, so the relationship of determinant and eigenvalues is such that the determinant for a diagonalizable matrix is the product of eigenvalues. Okay, and if I have a diagonalizable matrix and I take the trace of it, means I'm taking the trace of V lambda V inverse, I can use this property here, right? I can flip the V over here to the other side, because V is invertible, V inverse V is identity. So the trace of A is the trace of the matrix of eigenvalues. Okay, well, what is the matrix of eigenvalues? That means lambda 1 plus lambda 2 plus and so on up to lambda n. So that's the sum of eigenvalues. Isn't that cool? Because it's even cooler than the determinant, I think, because the trace is so easy to compute, right? What is the complexity of computing a trace of an n by n matrix? Computational asymptotic complexity. Yeah, it's like so simple algorithm. ON, right? If I n by n matrix, I need to just n operations, just scan the diagonal, sum them all together. I don't even need to look at the entire matrix. I can completely ignore what is off diagonal, right? I don't even need to read the entire matrix. Yet I can compute what is the sum of eigenvalues. So if somebody gives you a matrix and asks you, hey, what's the sum of eigenvalues? You would be real stupid to go to compute the characteristic polynomial and then find the roots of the characteristic polynomial and then sum them together. Because all you need to really do is to sum all the elements on the diagonal and you already got it. Now, for a diagonalizable matrix, of course, there's this little catch. If it's like one of these defective matrices, then this would not work. Okay, so let me, I guess, conclude by putting this together. So I said there's one more thing I want to, I guess, caution about. So I said that the product of eigenvalues is the determinant of A, right? And the sum of eigenvalues is, again, I'm assuming diagonalizable matrix is the trace of A, okay? So I assume that the matrix A is real, okay? But of course, sometimes it can happen that I need complex eigenvalues, right? We discussed that before. So what happens if I need complex eigenvalues? Well, that seems weird, right? Is there some contradiction? Because here I might have some complex numbers. My eigenvalues can be complex, okay? But my matrix is real, right? So for real matrix, determinant must be real. And of course, trace must be real. I'm just summing real numbers. There's no way how complex numbers could appear there. They can appear in the eigenvalues, right? Because in the eigenvalues, sometimes I must take the square root of -1. That's how I get the complex numbers there. So is there some contradiction? Because on the right-hand side, we always have real numbers. And on the left-hand side, we will be summing or multiplying complex numbers. Do you see where is the... Is there some problem?
Aren't the complex numbers pairs?
Exactly. That's exactly what I wanted to hear. That's the right idea, because that's the cool thing about the complex eigenvalues. If that's what we said the last time, right? If lambda is an eigenvalue of A which is complex, then lambda complex conjugate is also an eigenvalue. Okay. And the cool thing is if you multiply them, then you get just the norm of lambda squared, right? Which is a real number. And if you add them together, what do you get if you add complex number and its complex conjugate? You get twice the real part of lambda, right? So the imaginary part is going to be 0. So you get, again, real number, Or I guess I could write it like this, right? So indeed, there might be complex numbers here, but in the product or in the sum, because of this property that for lambda there is also lambda complex conjugate as eigenvalue, this always, indeed on the left-hand side too, must be a real number. So everything is cool. By the way, I guess for a 2x2 matrix, this already tells you how to compute the eigenvalues and eigenvectors, right? Because you can compute their product and their sum. There could be a little problem if it's not diagonalizable, but again, the problem will go away the moment we go to symmetric matrices, and that's sort of the idea of a single value decomposition. So we will get there. Okay, before we get there, we have another application of eigenvalues and eigenvectors, and this is a very fundamental and very important application: simple differential equations. Have you had some differential equations before? Or do I have the honor to be the first to that thing? So I like to start always by the geometric idea. So before we get to the actual equations, I'll sort of like just draw a picture what the idea is about, okay, or what is going on there. So the differential equation looks like this. So it tells me that a derivative of some function, or is, okay, let me write this down, then I will explain it. So differential equations compared to all the regular algebraic equations we were working with before, like for example, like finding the roots of a characteristic polynomial, that's like a standard algebraic equation, right? And the solution of standard algebraic equation is a number. Okay, it can be a real number, it can be complex number, but it's a number. The solutions of differential equations are what? Do you know if you had it before? Not numbers, but functions. Okay, so we are looking for a function. In the simplest case would be just like a 1D function from reals to reals, right? Or maybe I can like limit the domain from like 0 to infinity or something to reals, or maybe just an interval. Doesn't matter. What matters is that I'm looking for a function. Okay, function that satisfies some properties, and these properties are exactly the differential equation. Okay, and differential equation, because the properties involves a differentiation of the function. So this, I guess, is like the simplest prototype of a differential equation, and then from this you can get infinitely complex, but we'll look at the simplest case. So what the equation says, this means that I'm looking for a function y such that its derivative satisfies certain constraints, certain equality, okay, at every point t. So the t is sort of like the parameter, that's the parameter here. And the function f, this f thing here, that's a given, that's a specified function, that's a lot like the input. If somebody asks you to solve a differential equation, then they have to tell you what this f is, basically. That's sort of the contract, okay? And what the f means is, for a given y and t, the y is sort of like is the function of t, but I guess it sort of helps to sort of like abstract yourself from the t for a moment. And it's a function that for a given y and t gives you a number, right? So I guess the f is nothing but like a function from r to r in this case. It gives you a number, and the number needs to be the derivative of the function at the point t. Okay. So you can be, I guess, you can be looking at it purely like as a mathematical intellectual exercise. Basically, you have a constraint, you have an equality for a function, and you have to find the function. Okay. You can stop right there, and you can like reason about it, right? But the really cool thing is that this has like a beautiful geometric interpretation. So let me try to sketch it here in this 2D or 1D case actually, right? But so if this is my parameter t, and this is my y, okay, and I will be looking for the y as a function of t, okay. So what I want to find is some function that the y will be a function of t, okay. And now the interesting thing is what the f tells me. So the f consumes t and y and tells me the derivative, okay. So I can visualize the derivative as like a little arrow, right? So what does it mean? If I'm here, let's say this is like 1, 1, t1, y1, and this would be f11, okay? It tells me what the derivative of the function y, that's the function I'm looking for, would be at t equal 1, if this is 1, okay? If I look somewhere else, then I might get some different derivative, right? Here maybe I'll get a derivative like this. Maybe here I will get a derivative like this. Every point in this plane will get a derivative through the function f, okay? That's the idea of a differential equation, okay? And then solving the differential equation means that somebody gives you an initial condition. So let's look at initial value problems. Let's say, and the initial condition means it tells you where the function starts. They tell you y0, okay? So let's say that y0 is here, for example. Let's say that somebody, again, like the contract would be that somebody tells you what the y0 is, or you can think about it like you can sort of solve it generally for any y0, and then you can plug in whatever y0. Never mind. Let's just assume that somebody tells you what the y0 is, okay? And what you have to do if you are going to solve a differential equation, you have to find the y. You have to find a function such that at every point the derivative of the function, at every point t, the derivative of the function matches whatever was specified by the function f, okay? So this interpretation is sort of cool. You can imagine like the vector field. It's a vector field in a plane, right? This function f, because every point in the plane, actually no, it's actually a scalar field in this really toy case. Never mind, but it assigns every point in the plane a value of the derivative, okay? So if I visualize it using these arrows, you can sort of imagine this is like an ocean current map or something like that. If you have seen like the flows in Google Earth, there are some pretty cool flows, right? So that's sort of like that idea. I mean, you would normally go to like R2, so you can have any arrows, but let's just keep this, I just want to keep this 1D. So the solving differential equation essentially means that intuitively that I drop a particle here, that's my initial condition, and then I let it advect through the ocean current, okay? And the trace of the particle it traces, or the path of the particle it traces as it's being advected through the current, that's the solution to the differential equation. Okay, so it's very beautiful. Pretty much all physics is expressed in the language of differential equations. So here we're going to look at the simplest case, linear differential equations, because their solutions are, guess what? They are systems of linear differential equations. Their solutions are described using eigenvalues and eigenvectors of a specific matrix. So let's get there one step at a time. So let's first look at this simple case. I guess that's like the simplest differential equation you can be thinking about. So in this case, so again, this is just you can use all sorts of notations for the derivatives. So this d over dt, that's the same symbol as I used here. In both cases, it means the derivative of y with respect to t, right? The y doesn't have any other parameter here, so there's no question what I'm differentiating about. And this right-hand side, that's my function f. So this is a specific function f. That's the simplest possible case I can pick, okay? So here, my function f just takes the value of y and multiplies it by a, which is a constant. Somebody told you what that constant is, okay? Let's try to plot this one as this current map, or whatever you want to call it. Let me try to plot it here. So if here again goes my t, here goes my y. So what is this function a? Well, in this case, the function f yt, it doesn't even depend on t directly, right? It only depends on y, and it's just a times y, okay? So how the arrows would look like in this case. So if, for example, if a, let's assume that a is 0.5, okay, to make it a little more concrete. So if I'm at 1, then the arrow will be like pointing like this. I want the derivative here to be 0.5, okay? If I'm at 2, then the derivative will want to be 1, right? So that means that the slope of the function at this point will want to be 1, okay? If I'm at 3, I guess I will get something like this, and so on, okay? If I move a little bit further in time, how this is going to change? Sorry, this is supposed to be parallel. Not at all, right? Because it does not depend on t. It only depends on y, right? Don't get confused that the y will eventually depend on t, because as far as the function f is concerned, it doesn't matter if the y depends on t or not. It's just a function of parameters y and t, okay? So here the function will be actually exactly the same, or the slopes at some other time t. Doesn't matter where I moved here. I could move just here or anywhere. It just, all right, let's say I move here. Again, I just draw another parallel line. Same idea, right? Exactly the same slopes everywhere, okay? So this is I guess the simplest case of a differential equation. So, and if I start with some initial condition, let's say I start with y0 equals 1, what do you think the solution is going to look like? Just looking at this like geometric picture. Huh? It's going to shoot up, right? Like it's going to be something like this. Oh, I guess I shouldn't have. Yeah, no. It doesn't have to pass through here, right? It's going to pass through somewhere else, right? So basically the idea is the higher I get, the faster I sort of accelerate up, right? So this geometric intuition can be easily supported by mathematics, because here, this is one of the rare cases of differential equations where you can actually solve it analytically, because here the analytical solution is sort of trivial. So I guess I could, you know what, let me first write it in a little bit different way. The solution is exponential function, okay? So the solution is y t equals c, where c is some real constant, okay? E a t. So where e is the exponential function, a was the constant here, so a is some arbitrary real constant. T is my parameter of the function, and again c is a constant, okay? But it's sort of trivial to see that for any, I could just put c to be 1, but then I'm sort of missing like lots of solutions. I want to find all solutions. So it's sort of trivial to see that if I take the derivative, what do I get if I take the derivative of this function? So the constant just gets copied, right? Yes. A, E, A, T, right? Well, that happens to be exactly the same as A, Y, T, right? Because these are just constants, so I can flip them, and this is A times Y, T. So indeed, this is a solution, right? You can just see it trivially. Just take the derivative, aha, matches, solution done, right? If you were looking at it from like the purely mathematical standpoint, now that's basically the end of discussion there, okay? And you know that how exponential functions look like, right? Depending on the exponent, like this. So it matches exactly our intuition that something that sort of shoots up very quickly, right? I mean, it doesn't have to shoot up that quickly, right? If A is small, like if you have interest on a savings account, you know, it doesn't really grow that dramatically, because in that case the exponential is more like this, right? But for higher A's, it shoots up very quickly. If you had 100% interest, you would see that. Okay, so yeah, the concept of initial condition. So this C essentially parameterizes the solutions, right? The one way I can give the C some reason is I can look what is the Y at 0. So just substitute 0 for T. And what I will get, well, what is this? It's e to a 0, right? So that's e to 0, which is how much? That's 1, right? As far as I know. So the C, the parameter C, is actually exactly equivalent to where the function passes at value 0, at t equals 0, okay? So if I'm given an initial condition, if I am told what y0 is, then I immediately know what C is. Okay, so that means that if I'm assuming the initial condition, you always have to assume something like this when you are solving differential equations. It doesn't always have to be initial value problem. You can also be dealing with boundary value problems, and so on. It could be higher order. But let's just cover the basic case here, and let's just assume we have an initial value problem. Okay, so the interpretation is to like drop a particle into like an ocean current somewhere, and where you dropped it, if I dropped it here, I would have some different solution, right? and they are just, in this case, they are just a scalar multiple away. Okay, so that's the solution of this, I guess the most basic differential equation. And now we are gonna take this to matrices, and that's where eigenvalues and eigenvectors start being useful. So let's first remind ourselves what's the power series for exponential. Okay, I think I was saying that that's one way how you could like define exponential, right? As this infinite series, or like Taylor expansion of exponential, whichever way you want to look at it. Nevertheless, this is true. And this will be important when we will go to a system of linear differential equations. Then we will essentially generalize it to exponential of the matrix. It sounds scary, but it's actually not that difficult at all once you know eigenvalues and eigenvectors. Okay. So this case was like the 1D case. I was sort of even struggling with these arrows here, right? Because here, what I can do with this model, I can do like shooting straight up, right? Because then I would need a derivative infinity. That's usually not good, right? So what I would probably need if I'm already to model like an actual ocean current, I would probably need to consider like a two-dimensional function. Okay, and that leads to vector differential equations. So the idea is basically the same, except that the function we are looking for now, so we are again looking for a function, but this time we will be looking for a vector function, okay? No, sorry, the other way around, like this. So maybe I can like denote it like this, that's like a vector function. And you can look at it basically as a composition of two functions, y1 and y2. So now these are like vectors, but they depend on some parameters, so they are functions. So here y1 and y2 would both be just regular functions from R to R. Okay? So those are the components of a vector function. Yeah, I guess that's what I would probably do if I wanted to do like an ocean current, right? So I would had an actual vector function, so I can be also going like straight up. Well, never mind. Let's look first at the mathematics of this, okay? So I have a system of linear differential equations. So that one's if I take the derivative of this vector function, well, the derivative just means differentiating it per coordinates, right? And I consider this the same idea as here, right? So the first one needs to be multiplied by some lambda 1 and the other one by some lambda 2, okay? So this is really nothing but just taking two regular differential equations, okay? You might be like wondering why I'm sort of making it complicated, because, well, I want to just bring it to a matrix notation first, and then we will actually turn it to actual system of linear differential equation. So this would be basically two unrelated one-dimensional differential equations, okay? But nevertheless, I can still write it as matrix vector multiplication and sort of pretend that I'm solving like a two-dimensional differential equation for a vector function, okay? But the solution, of course, is just like solving for every component independently, right? But again, let's write it in the matrix form like this, okay? So this would be e to the lambda 1t, y1, 0. That's my initial condition on y1. This is my initial condition on y2, okay? And now the more interesting case is when we don't have a diagonal matrix there. So when I'm, again, looking for a function, so y, let's say that the matrix A is a 2 by 2 diagonalizable matrix, and y is a, y is a function like this, with two components, y1 and y2. And now this is a more interesting case. I'm solving non-trivial 2D differential equation, where I say that the derivative of y, that means differentiating each coordinate separately, needs to be equal some matrix times the function itself. Okay. So sort of the same idea as here in the 1D case, except that I sort of this y is now a 2D vector. So this y is also a 2D vector, and the scalar became a matrix. Okay. So that's sort of like a matrix version of that, a system of linear differential equations. Okay. And how do we solve it? We solve it using eigenvectors and eigenvalues, assuming the matrix A is diagonalizable. So the way we are going to do it, let's see. We are going to use the eigenvalue decomposition of A. So we plug there B lambda V inverse instead of A. And because V is invertible, what we can do is we can just multiply from the left with V. Okay. So because the V is constant, it doesn't matter if we write it here or inside. So we can as well stick it inside. Okay. And that's how we get this form. And this is begging for a substitution, right? Because you have this term here and this term here, which are the same. So I will say, well, let's call this a new unknown. Let's call this ZT, right? And Z's still going to be a function from R to R2. So I have simplified, or I have converted the original problem into a different problem, into this problem, that the derivative of Z is the lambda times ZT. But lambda now is a diagonal matrix, right? It's the matrix of eigenvalues. Okay. So this is actually the simple case, right? Because in 2 by 2, the lambda is just a matrix like this, lambda 1, 0, 0, lambda 2, okay? So solving this differential equation, that's trivial, right? I just put their exponentials of the diagonal, okay? And here, my initial conditions at 0. Those are just whatever values I get to pick, okay? So that means that I have solved the ZT. And from the ZT, I can go back and get the solution for the original problem. That's the YT. Because here, look, ZT was V inverse YT. So if I multiply this from the left with V, again, V was invertible. That means that VZT is YT. That's how I get my original solution, okay? So my original solution I get at V times Z. And Z, I know what that is. That's this, right? Again, I can use the same argument for y0, and I will get to this form. This is my solution. And it turns out that this key matrix here that gives me the solution of a system of linear differential equations, that's actually nothing but a matrix exponential of this matrix A I started with. Okay. So let's take a look at matrix exponential. I think that's going to be the last thing we talk about today. So the matrix exponential is a direct generalization of the exponential of a scalar. That's what I had here. Okay. Nothing prevents you from putting, instead of scalar a matrix, right? So that's what we do here. And we say, well, that's now an exponential of a matrix. Now we have to prove that it actually converges and gives you something reasonable, but you can actually do that. You can prove that. And even more importantly, if the matrix is diagonalizable, notice what happens to the powers. Okay, if the matrix is diagonalizable, you know, it's V lambda V inverse to the power of K. Well, what's going to happen, for example, for K equals 2? And I do V lambda V inverse times another V lambda V inverse, right? But this is identity, right? So what I'm going to get here is V lambda squared V inverse, right? If I keep doing that, all I'm gonna keep doing is taking powers of the lambda inside, okay? So all the powers of A, they have just this form, okay, including the identity. Identity you can just also write as VV inverse, right? Which means that the entire exponential you can essentially write like this, as V times the exponential of the matrix of eigenvalues times V inverse. Okay, and if you compare it to our solution of the differential equation, where was that? Here. you can just write here the exponent instead of the V and this matrix and B inverse, you can write there the exponential of A times T. The times T is important there, okay? Y0 are still your initial conditions. Now the important thing is that you multiply the matrix A by T. And I have a cool example of how this works in practice, which also illustrates why the complex eigenvalues and eigenvectors are actually useful. I will do it on Monday because it takes a little bit, but if you want to think about it already, try to work it out. What does it mean for this matrix? 0, -1. I guess that would be a good, another homework. Maybe next time I will do homework or something on that. But what I'm going to do, I will just show you this example the next time. But if you want to do extra homework, which I'm sure you do, then you can work it out for this matrix. And think about what this matrix does, actually. And I will show you the solution on Monday. Okay? Any questions?
There's homework due this week, right?
Sorry?
There's homework. Is there homework next week for next week?
Yes. There's homework too. I posted it yesterday. It's some sort of practice of determinants, and I think one example of eigenvalues, eigenvectors. So this is like a non-mandatory homework, but also cool. Okay? Any other questions? If not, then you can go home.